All right, here we go. This is the first lecture after Exam 3. We're in Chapter 5, talking about gases and their properties. Let's just get right into it, okay? Now, relative to other types of matter, solid, liquid, and of course gas, gases have some unique properties. Solids and liquids, unlike gases, are unable to fill the volume of their container. Liquids are able to take on the shape of their container, but not to fill it completely. And so gases can assume both the volume and the shape of their container. Gases are also the most compressible state of matter. What that really means is that we can take the volume of a particular gas and squeeze it down, and still have all of the gas that we had at a larger volume, but just hold it in a smaller, more compact volume. Gases, because they move very quickly, are able to mix very well with other gases, and so if we have a mixture of gases, we can assume that they are mixed relatively completely, as long as they've been given time to equilibrate. And lastly, they have much lower densities than liquids or solids. We know, for example, with water, has a density of about 1 gram per milliliter, right? Solids, steel, for example, has a density of about 8 grams per milliliter, and so a little bit more dense. But gases have densities that are much, much lower. They're on the order of 2 grams per liter. So not per milliliter, but per liter. So 0.002 grams per milliliter. So almost 1,000 times less than that of something like water. Okay. This picture here is an image from our textbook. It's just nitrogen dioxide gas. It's a dark brown colored gas. And you can tell that it's both filling the shape and the volume of that volumetric flask that it's in. When we talk about gases, one of the things we're going to focus on is the pressure of a gas. Now, pressure, for you physics people, is the force that's being applied divided by the area over which that force is applied. And so when we think about atmospheric pressure, for example, you can tell in this image here, the pressure of the atmosphere is the mass, the force of all of the air that's over a certain area of ground, of surface area of the earth, right? And so in American units, the common pressure is 14.7 pounds per square inch. We call it PSI, right? But really that's pounds per square inch. And so for every square inch of surface that we see on Earth, there's 14.7 pounds of air and gas above that square inch. Now, the SI unit for pressure is a Pascal, Newton per meter squared. We don't use that a whole lot because it's actually kind of a tiny little unit. The unit that we use much more often is the atmosphere, and you can see here that 1 atmosphere is 100,000 pascals, and so we'll stick to atmospheres. We might see torr or millimeters of mercury. If you'll notice here, those two units are the same value. They have the same size, but they're just different in terms of how we talk about them. Torr versus millimeters of mercury, same value. Just know that it's 760 torr for every atmosphere, 760 millimeters of mercury for every atmosphere. So, let's do a quick example. Here we have a question. The pressure outside a jet plane flying at high altitude is considerably below standard atmospheric pressure. Therefore, the air inside the cabin has to be pressurized in order to protect the passengers. What is the pressure in atmospheres of the cabin if the barometer reading is 688 millimeters of mercury? So we're looking for it in atmospheres. We have it in millimeters of mercury. One quick thing, this barometer here, that's just an instrument that's used to measure pressure. Okay, that's what we call that. And so we're going to start with the thing that's not a conversion factor, like always, 688 millimeters of mercury. And we're going to convert that into what we want. We want atmospheres. And we know from the preceding slide that 1 atmosphere is 760 millimeters of mercury. Our units cancel. And we are left with, let me pull out my calculator here, 0.905 atmospheres. Okay, so I'll go back to the previous slide for just a second. The equivalences that you really need to know is this one, right? 1 atmosphere, 760 millimeters of mercury. 1 atmosphere, 760 torr. We're going to use those when it comes to doing some conversions. Okay. And so we have here Boyle's law, and Boyle tells us that there's a relationship between the pressure and the volume of a gas. So if we start here in the middle, as we decrease the volume, the pressure must increase, right? So we have a higher pressure. If we look at our little gauge here, it's here instead of here. The volume of our container has, the volume of our gas has gotten smaller. If we lower the pressure out here, then the volume of our container, so the volume that our gas occupies, has increased. And so this pressure is proportional to 1 over the volume. That's an inverse relationship. We increase the pressure, but the volume goes down. Here, we decrease the pressure, but the volume goes up. Right? So, let's take a look at another one of these laws. That was Boyle's law. Charles's law looks not at pressure and volume, but at temperature and volume. And so, if you'll notice here, all of these are at exactly the same pressure, right? The pressure doesn't change. But what's happening is that as we lower the temperature, our volume gets smaller. As we raise the temperature, our volume gets larger. And so instead of being an inverse relationship, this is a direct relationship. And so temperature is directly proportional to volume. Okay? Charles also noted the relationship between if we threw pressure into the mix. And so if you'll notice, all of these containers have exactly the same volume, right? But what we notice is that here we lower the temperature and the pressure goes down. Here we raise the temperature and the pressure goes up. And so temperature is also directly proportional to pressure. Okay? All right. The last law that we need to take care of is Avogadro's law. Avogadro, we know him for his number, right? The number of particles in a mole of something. But the law, the gas law that is named after him, has to do with the volume of a gas and the number of particles of that particular gas. And so here, again, we're going to start in the middle, right? And as we move left, we remove gas. We're removing gas particles. Do we measure gas particles individually? Not really. We measure and we look at the moles of a particular gas. And so the number of moles goes down. That's our N. N is the abbreviation we're going to use for moles. Not abbreviation, the variable that we're going to use for moles. And so as the number of moles goes down, obviously you can see that the volume has decreased. Similarly, as we increase the number of moles, if we counted up all these dots, there's more dots here than are in the original container. as we increase the number of moles, we increase the volume of that gas. And so the number of moles is, again, directly proportional. The number of moles is directly proportional to volume. Right? Again, what that helps us do is it helps us sort of combine all these together. And so, again, you know this as the ideal gas law, or the ideal gas equation. From those three laws that we saw, Boyle's law, pressure is inversely proportional to volume. Again, that has to be a constant number of moles and a constant temperature. Charles's law tells us that volume is directly proportional to temperature if the number of moles and the pressure is constant. And Avogadro's law, where we know that the volume is proportional to the number of moles if pressure and temperature stay constant. If we sort of collect all of these together, and we use volume here as our common factor, volume is proportional to, well, it's proportional to T, it's proportional to N, and it's proportional to, we can rewrite this as volume is proportional to 1 over the pressure, and so volume is proportional to the pressure. Whenever we use the proportionality, we know that we can replace that proportionality with some constant that we multiply by our value. And so V is equal to some constant times this set of variables, temperature times moles divided by pressure. If we rearrange this a little bit, and if we give that constant a letter, let's give it the letter R, then what we end up with is P times V, move that P over, equals R times Tn. Now, for whatever reason, we have come up with a different order for writing these, and we end up with PV equals nRT, the ideal gas law. Let's do a quick problem or two with this, and then we'll end this video. First, for a lot of these gas problems, we're going to sort of set a standard condition, and that condition we call standard temperature and pressure. It's 0 degrees C and 1 atmosphere are our standard temperature and our standard pressure. 0 degrees C and 1 atmosphere is set as STP, standard temperature and pressure. Okay? So if the standard temperature and pressure is 0 degrees C and 1 atmosphere, then we're going to plug all that in to our ideal gas law. PV equals N times R times T. We have atmospheres, we have temperature. So this is 1 atmosphere, 0 degrees C. If we say that it's for 1 mole, and experimentally, this gives us a volume of 22.414 liters. Then we're going to solve for R. Now, I want to stop right here and make a point about temperature. The Celsius scale can have negative values, right? Because of that, we cannot use the Celsius scale when we do these gas law problems. We can't have negative pressures, negative volumes, or negative numbers of moles, so we also need a temperature scale that doesn't have negative values. So we will use the Kelvin scale. So temperature must be in Kelvin. So Kelvin is equal to our degrees C, our centigrade, plus 273.15. And so for us, 0 degrees C plus 273.15 means that we have a temperature of 273.15. In reality, if you drop that 0.15, it's not going to change things a whole lot, and so I'm okay if you just do 273 for most of these problems. So we're going to scratch out that 0 degrees C and put 273 Kelvin. Okay? So let's solve for R, that ideal gas law constant. We're going to rearrange a little bit, and we end up with PV over NT. That's 1 atmosphere times 22.414 liters divided by 1 mole and 273 Kelvin. Right? Now, if our math works out, we should end up with an R value of 0.0821. We have to pay special attention to units. As with all constants, they have to have units. And this one has some pretty crazy units. If you'll notice, we have atmospheres times liters on top and moles times Kelvin on the bottom. And so what we end up with, the way that it's usually written, is liter atmospheres per mole Kelvin. Okay. Now, remember this, write this down, commit this to memory if you haven't already. That value for R is the value that we'll use throughout Chapter 5 until we get to kinetic molecular theory. So, one quick question, and then we'll stop this video. So, sulfur hexafluoride is a pretty heavy gas, SF6. This question asks us to calculate the pressure in atmospheres if we have 1.2 moles of this gas with a volume of 5.43 liters at a temperature of 69.5 degrees C. One thing that I'll point out, a lot of times in questions, they'll say that it's a steel vessel or a hard-sided vessel or something like that, so you know the volume can't change. If the question says a balloon or something along those lines, then the volume does change, and often the question is asking you to solve for a new volume. So, PV equals nRT. What are we solving for again? Pressure. So we're going to rearrange this to solve for pressure. We have 1.82 moles. We have R from the previous slide, 0.0821 liter atmospheres per mole Kelvin. And we have a temperature of 69.5 degrees C. Let's convert that real quick. 69.5 plus 273.15. And so we end up with a temperature of 342.65 Kelvin. I hope that doesn't get cut off the screen. And we're going to divide by volume, 5.43 liters. Right? When we solve this, we end up with a pressure of 9.42 atmospheres. Okay? So it's just figuring out which of those 4 variables is the unknown variable and then solving for it. Okay? Alright, that's the end of this first video. I hope it went okay. If you have any questions or anything, either come to the Zoom office hours on Monday or shoot me an email. Take care.